In order to introduce briefly the theme of the day, I quote Paul Edwards from an article on the history of climate modeling. Starting in the 80s, climate modeling has moved in the direction of increasingly comprehensive models. Earth system models couple atmosphere ocean to models of other climate-related systems, such as the land surface, the cryosphere, hydrology, and vegetation. Meanwhile, integrated assessment models emerge from an environmental impact modeling tradition dating to the world dynamics models used in 72 Club de Rome reports, the limits to growth. So we have the great opportunity today to start with one of the authors of the Limits to Growth, Professor Dennis Meadows. So Professor Meadows, please.
Good morning, everyone. So I'm happy to be here again. Albert, thank you so much. And thank you for the invitation to join you in this seminar. I yesterday gave some comments about how to help people understand better some basic concepts of communication. And today I will start to talk about communicating what? Communicating about climate change models. I'm going to speak about modeling long-term climate change, and especially the influence of long-term global dynamics. Dynamics means behavior on climate change. My goals for this session are the following. I'm going to define some basic concepts that are relevant to all of the models. From 1972, when we did our first study, until today, of course, computers, the scientific understanding, and the methodology of computer modeling have all made enormous changes. But these basic concepts haven't changed. They were good in 1972, and they are still useful today. And as you listen to other speakers in the rest of this meeting present different kinds of models, the concepts I'm about to give you will be helpful in understanding and asking questions. I'll indicate the important role that time constants play in modeling climate. There's enormous difference between weather reports and climate forecasts, and it has to do with time constants. I'll discuss that. Describe the nature and interaction of physical, biological, and political factors in long-term climate models, and introduce the potential role of some tipping points. Then finally, if we have time, just at the end, I'll show how, even though we didn't put climate change in our 1972 model, it has some obvious consequences. I need to be clear. I will not today teach you any particular modeling method. I have taught modeling methods for many years, but there are so many different ones. They're all useful in some ways, and it takes a great deal of time to master them. So not interesting today. I am going to forget about or overlook short-term and medium-term climate models and just focus on long-term models. Short-term and medium-term are important, but they just serve different functions. I'm not going to describe the specific equations in any of the climate models that I've made, although I'll show you some of the main causal assumptions. And I'm not going to evaluate the current state of the field of climate modeling. Of course, it's evolving and getting better, hopefully, every year, but that's outside my scope. So what are some basic concepts for modelers? The first is behavior mode. Behavior mode is the behavior pattern that you're trying to understand. And generally speaking, when you build a model, which is tracing behavior over time, you organize it so that it shows some past behavior. You compare that with history to see if the model is plausible. And then some future behavior, which is of course why you built the model, is to understand what might happen and how you might intervene to make things better. The time horizon of the model is the period of the behavior mode. I'll illustrate that in just a moment. A key concept in climate modeling is the difference between stocks and flows. They tend to get mixed up, and when people confuse them, they can make some very common mistakes. I'll define them in a moment. Stocks are things like the heat in the atmosphere, the amount of water in the ocean. Flows are things like emissions of CO2 into the atmosphere, the radiation of heat back out of the atmosphere, the flow of rivers into the ocean, and so forth. So stocks can be evaluated at each point in time. Flows have no meaning at an instant. They only exist over time. Climate change, of course, is inherently a dynamic of stocks and flows. The flow of carbon dioxide and other greenhouse gases is going up, and that raises the stock of CO2 in the atmosphere, and with falling consequences. A key issue for modeling is, what do you put in and what do you put out, leave out, or forget about? And if you put it in, how do you treat it? It's the difference between endogenous, exogenous, and excluded variables. Again, I'll illustrate that in just a moment. And once you know the variables, then implicitly you define the conceptual boundary of the model system. And a key question that anyone listening to this lecture today may be asking over the next couple of weeks is that particular issue inside or outside the boundary of your model? If it's outside, it means it's not being considered. And if it's inside, it means it's having an influence, and you should be worried about what that influence is and how it's represented. So let's talk first of all about varying time constants. Yesterday, I showed this graph, which is the amount of CO2 in parts per million in the atmosphere from about 2005 up to 2021. And it raises over that period from 380 parts per million up to about 420 parts per million. Now, we could make a model of that. And if we did, it would have some useful information for us. But notice, if we made an excellent model of this behavior, it wouldn't show us anything about what the same variable, CO2 parts per million, has done over the past 1,000 years. The factors that are influencing this behavior are totally different than the ones which are influencing this behavior. An excellent model for this would be a lousy model for that, and conversely. So when you start to think about a model, first question you have really is, over what time period do I want to understand the variable? Let's take global temperature, since that's often used as a way of talking about climate change. Here's another graph. Here now, the time horizon is 140 years from 1880 up to 2020. And again, it's the same variable. Well, this is temperature in degrees centigrade. And what you have here is actually the 4 different measurement series. They differ very slightly depending on how and where the measurements were made. But you can see generally these 4 different things, NOAA, NASA, Berkeley, et cetera, are in pretty close agreement. For a modeler, the important thing to see in this is that there are actually 3 different, very different time pattern, behavior modes. There's the yearly behavior mode. You can see it in the short-term things. This is the kind of change which occurs year from year. Then we see in this time graph some decadal behavior modes. You see here the sinusoidal behavior. And then finally, the centuries-long behavior modes. This is really weather. This is the factors which influence changes in weather from year to year. Here we get off into some of the global geophysical processes that have time periods of 10, 15, 20 years. And here, of course, is the underlying behavior mode that we're often thinking about, climate change. When you want to understand the differences between these three, you turn immediately to this issue of stocks versus flows. Stocks are accumulations within the system. If you don't need to be a scientist to recognize stocks. If you look out your window, you will see stocks, a number of trees in your yard, or number of people on the sidewalk, or whatever. And flows are how those stocks change over time. So flow would be, in the case of the forest, the amount of wood which is being added per day. For pedestrians, it's in people walking into your neighborhood versus the number walking out, and so forth. One way to understand the difference is that stocks can be evaluated at a point in time. If you just imagine stopping the system at a point in time, you can count what the stocks are. Flows cease to exist. They have no meaning at an instant in time. They only exist over time. And in the climate change system, some of the stocks that we would expect to see in models are, for example, tons of CO2 in the atmosphere, or this may be expressed as CO2 concentration if you divide through by the volume of the atmosphere. Square miles of ice surface on the planet, that's very important because it determines, it's an indicator and it also influences thermal dynamics. Cubic miles of or water in the ocean, which of course has a bearing on sea level and so forth. Important flows affecting the climate change, emissions and deposition of CO2. CO2 is put into the air and is taken out by weathering of rocks and so forth. Formation and melting of ice, flows of water into the ocean from ice melting, and loss of water from the ocean from evaporating. Those are some of the flows that you would expect to see. And modeling climate change becomes trying to quantify these and figure out their interactions. Now, since we're not going to be getting into specific modeling methods today, I'm going to use a simple analogy to help understand this. The bathtub. Most people are familiar with a bathtub. Stocks and flows can be understood by imagining a bathtub. The water in the tub is the stock. It could be high or low or zero. And it has limits, of course. You can't overflow the bathtub. The flows are those things which influence the level of water in the bathtub. The principal flows are the water coming in through the faucet and the water moving out through the tub drain. Other possible flows would be evaporation of water from the surface or leakage if the tub is cracked. Now, in real systems, the stocks and flows may be tangible, like water, or in the case of climate, like CO2. Those are things you can, in theory, see and feel. Or they may be intangible, like information, expectations, political will. But in the same way that you can talk about water going up and down, you can talk about your expectations going up and down. How optimistic are we? How resolved are we to do something? These are important flows. So let's just think about the bathtub here. Sorry for my rather primitive graphics. This is the level of water in the tub. As long as the water coming in is greater than the amount going out, the level will be increasing until it hits its limit. If you want the water level to go down, you have two choices. You can increase the outflow rate, or you can increase or decrease the inflow rate. Same thing with climate change. If we want the CO2 level to quit growing in the atmosphere, then we either need to reduce the emissions or increase the rate at which it's removed. And for the moment, this is the area where we have the most realistic control. Now, let's convert this over to modeling and more to climate change. I mentioned different types of variables: excluded, endogenous, and exogenous. An excluded variable is one which simply isn't included in the model. It doesn't show up. It doesn't appear in any of the equations. It's not the basis for discussion. In this case, although some may think it's very important, cloud cover is excluded. You notice that there's no influence from cloud cover going in to influence the heat. Here's an exogenous variable, energy from the sun. We know that the sun has a regular sunspot cycle, and as the sunspots increase and decline in number, that has some influence on the amount of heat which flows out of the sun and into the Earth's atmosphere. So the energy from the sun does have an influence on the heat content of the atmosphere, but clearly it's exogenous. The energy from the sun does influence what's going on Earth. What's going on Earth has absolutely no influence whatsoever on the energy that's coming from the sun. That's an exogenous variable. Endogenous variables are the meat of the model. They are the ones which influence and are influenced by other things in the model. In some cases, it's direct. The heat content of the atmosphere has a very direct relationship on the amount that's radiated back out to space. And the amount that's radiated out to space has a very much direct impact on how much is in the atmosphere. In other cases, it's more ambiguous. We know that somehow the heat content of the atmosphere is going to influence how many, excuse this typo here, how many emissions we make. So I've just put here a dashed arrow saying there's some kind of influence. We don't know exactly what it is. But once the CO2 emissions are determined, they directly influence concentration. And as we'll see in a moment, that influences the radiation of heat out of the atmosphere. That is, incidentally, why CO2 is so important. It doesn't influence the amount of heat coming in, but it influences the amount of heat that stays in. Now let's imagine for a moment that we want to change our understanding of cloud cover. Here it's an excluded variable. We could make it an exogenous variable. We could keep track of it and represent its impact on the amount of heat that stays in the atmosphere. The way cloud cover does that, here at least it's shown, is that it tends to screen or trap heat coming in from the sun. So as cloud cover changes, the amount of heat that stays in the atmosphere changes. And we're saying, however, in this case, or implied by this, is that as the heat content goes up, it doesn't have any influence on cloud cover. In this case, if we wanted to make a model of this sort, cloud cover would be something that we would put into a scenario story. I'll describe that in a minute. And we have another choice. We could make cloud cover an endogenous variable. We could, in some way, say that the heat content of the atmosphere, because it influences evaporation and winds and so forth, influences cloud cover. And that of course, has an influence. The difference between excluded, exogenous, and endogenous isn't in the nature of physical reality. Physical reality is only one thing. The difference between those three variables lies in our scientific understanding of them. Initially, cloud cover was excluded. Nobody imagined or had any knowledge about how it could have an influence. And over time, we've come to understand that cloud cover needs to be brought in as an endogenous variable, even though our ability to model it so far is still very, very limited. There are many other things that are influencing climate. And again, I remind you, all of the models which you're going to be talking about and all the considerations you'll be talking about over the next 2 weeks need in one way or another to decide if they're going to deal with these or not. So volcanic eruptions put out particulates which block the sun. Probably, at least over periods of interest to us, volcanic eruptions are an exogenous variable. We don't understand what causes them, but we're pretty sure that the climate doesn't. Sandstorms, windstorms blown up in, for example, in Africa, coming across can block the sun and begin to alter the heat balance. Cloud cover, I mentioned. As we change our agricultural crop cover types, that has some influences on annual Notice I'm now talking about the things which can change year by year. They're responsible for that first behavior mode. El Nino, La Nina, the climate or the temperature patterns in the ocean. Again, we don't fully understand them, we measure them, but they rapidly change, and so they're responsible for annual variation. If I wanted to do not an annual model, but a model which shows that sinusoidal behavior over decades, I would go to a set of very different factors. I would go, for example, to sunspot cycles, waxing and waning impacts on the heat input. I'd start to look at the amount of the surface of the Earth, which is paved over for roads and parking lots and so forth. They alter the heat reflection. Doesn't change drastically year by year, but over a 10 or 20 year period, the variation is enough to start influencing change. That would have to be in a 10-year or 20-year model. Agricultural crop cover. The amount of forest cover is an important one, not only because it influences radiation, but also because it has some impact on the amount of CO2 that's in. So if I'm trying to model 10, 20-year changes in climate, I'd have to think about forest cover. And if I'm going to the very long models, ones mainly of interest here today, now we're getting off into a totally different set of factors. New energy technologies. There's about a 50-year cycle between when one energy form becomes dominant and it's replaced by another, from wood to coal, coal to oil and gas. Each of those took about 50 years and had enormous implications for emissions. The relationship between the storage and the release of methane, a big issue now is methane being released from the tundra. That's something which is unfolding over decades. The extent of ice cover, capacity of the ocean to absorb heat, and the action of ocean currents. Notice that some of these variables, although they change slowly over time normally, have the capacity to flip or to manifest a tipping point. I'll describe tipping points a bit later and show how they can have an influence. But the main point here is that you need, first of all, to understand the period of time you're trying to model climate change. And then when you do that, it will cause you to think what factors have to be put in. And I'll tell you as a professional modeler, it's a serious mistake to imagine you're going to create a model which spans several different time horizons. A model which is useful for you in analyzing day by day or year by year temperature changes is simply not going to give you good information about what happens over centuries. And conversely, a really good model of centuries-long change is useless when you try to think about what's going to happen tomorrow. It's kind of like a telescope, depending on which end of it. A telescope lets you look at long things, but it doesn't let you look at microscopic things. And a microscope is really great for looking at little things, short-term things, but is worthless for looking at the stars. And a model has that same general attribute. We don't only have to worry about the time period of causes, but also about the nature of the impacts. For us, some of the important impacts are biological, shifting climate zones. I'm a gardener and I'm confronted with the reality that I have to plant things earlier in the season now. Bleaching of corals is one of the big impacts from the change of temperature. Extinction of species, invasion of species. In some parts of the ocean are seeing invasive species move in because they need warmer water. And falling crop productivity. We used to think that CO2 going up would be good for food production, but it turns out that the temperature effects are probably more severe and they will start to reduce the amount of food that we can produce. So when you're thinking about climate change, of course, the reason is why are you worried about it? And if you're interested in a biological consequences, this would be some. In the case of economics, then it's things like the maintenance and repair of roads or coastal infrastructure, building dikes to keep the water from washing over your urban parks and so forth, flood damage, higher food costs, less reliable electricity. Insurance costs are going up or becoming unavailable even. Shifting demand for products. More people want air conditioners, fewer people want furnaces, speaking simplistically, but it illustrates the point. And the ratio of regional real estate costs. Areas in the Southwest of the United States are starting to understand that what lies ahead for them is fires and drought. And people are less inclined to move there than they were before. So my parts of the country, and let me say also Canada, are likely to face increased demand for real estate. These are just impacts of climate change. And then finally, there's the social impacts, which we're beginning to witness. Falling productivity of labor and capital because it's, amongst other things, more difficult to work outside, or because capital is tailored for specific conditions. Power plants require cooling water and were designed for a specific temperature. If the water warms up, the power plant must be operated less. The productivity of that capital goes down. Rising death rates from rising temperatures is going up. Greater migration pressures, more and more people finding they can't make a living where they are, they want to move. Less maybe of an importance for Canada, but an enormous issue now for the European Union and for the United States. More prevalent disease as pests move around. And then, unfortunately, we see it actually exacerbated now by the virus, but growing inequality between the North and the South. A key point is that each time frame has a different set of impacts and requires a fundamentally different type of model. So when somebody stands up and tells you about their model and what it's supposed to do, make sure that the impacts and the cause-effect relationship they built in are actually appropriate for the job. And now I'm just going to focus the rest of my talk on CO2, long-term changes. And as I said yesterday, I'm going to use CO2 concentration as a surrogate just to simplify the conversation instead of trying to talk about all the greenhouse gases. You might know, incidentally, that CO2 is not the most important greenhouse gas. The most important greenhouse gas is water. Water vapor traps more heat than CO2 does, but it's less under our control, ostensibly, and so we've chosen to focus on CO2. So the common idea about long-term climate change is as CO2 emissions go up, the biosphere health goes down. We extinguish species, crop productivity goes down, human health begins to fail. So there's a variety of circumstances. And the common idea is that when that gets to unacceptable levels, we'll start control policies. And those control policies will reduce the emissions. These negative signs, as I explained yesterday, means that if this goes up, this goes down. And conversely, if this goes up, this goes down, this goes down, this goes up. The policy implications of that idea, however, are that you can wait until you see biosphere health at unacceptable levels in order to begin your policies. One of our former presidents, George Bush, famously said, "When I see climate change, I'll do something about it." And he was basically ascribing to this point of view. But that common idea assumes that declining biosphere health is quickly perceived, that there's consensus about it, and that the consensus rapidly leads to effective policies. Those are both false assumptions, unfortunately, as we're beginning to see. Because there are three very important delays. There's a delay between when CO2 emissions go up and when the CO2 concentration goes up in the atmosphere. Remember that bathtub. The tub doesn't become immediately full once you turn on the faucet to full. You turn on your faucet to full, and it will take a while for the tub to fill up. Same thing with the atmosphere. So there's a delay between full-on faucet and full-up tub. There's a delay between raising CO2 concentrations in the atmosphere and the increasing amount of heat in the atmosphere. This is really like another bathtub. The CO2 concentration is in a way like acting like the faucet. It controls how much heat is coming into the atmosphere, and it takes a while for the heat to fill up. And then there's a delay between rising heat in the biosphere and falling biosphere health. It takes a while for a deteriorating ecosystem to begin impacting on human health, species diversity, food productivity, and so forth. Let me look at each of those in kind using the symbology of the kind of modeling that I do. Rising CO2 emissions increase the CO2 concentration in the atmosphere. Now, I'm using squares, rectangles, to represent stocks, and these little valves are flows. So this is the flow of CO2 into the atmosphere, and this is the flow out. And the concentration is just an algebraic expression. It's a different way of understanding the stock. If you divide number of tons into the volume of the atmosphere, you get the concentration of CO2, which, as you saw from an earlier graph, these days is rising and is up currently around 420 parts per million on average. The rising CO2 concentration in the atmosphere increases the amount of heat in the biosphere. Here again, I use this thing. Solar radiation heat is coming in. It accumulates as heat in the atmosphere. Normally, there's a balance. The amount coming in equals the amount going out. So the heat is constant. It's as if you adjust the drain on your bathtub to be the same, to give the same flow rate as the faucet. If you do that, the level in the tub doesn't change. And it doesn't matter how high the tub is full of water. As soon as the inflow equals the outflow, it quits changing. That can happen at a low level or it can happen at a high level. What's happened here is that as CO2 goes up, it reduces the heat radiation. It's like constricting the outflow on your bathtub. And so even though the incoming radiation doesn't change very much, this starts to go up. And rising heat in the biosphere reduces biosphere health. Here again, it's a kind of bathtub, although in this case, conceptually, it's even, at least for me, much more difficult to understand because it includes so many different kinds of factors. But the health of the biosphere is a stock. It has a, although we don't know precisely what it is, at any moment in time, there's a certain health which is slowly being restored by natural processes and is being reduced by the impact of climate change, wind, sea level rise, and so forth. And this health of the biosphere manifests to human society by species diversity, crop productivity, beauty conceivably, loss of ice, etc. It's vague and diffuse, different in different parts of the world, but generally as it deteriorates, it causes people to become concerned. So let's look at it as a bathtub. CO2 emissions goes up. That causes the CO2 concentration in the atmosphere to rise. There's some CO2 going back out, but as long as the inflow is bigger than the outflow, this will be high. As the concentration goes up, it reduces the amount of heat radiation. And if you reduce, if this was in balance and then you suddenly reduce the outflow, the inflow is going to go up and you'll have more heat in your atmosphere. That causes a wide variety of things, more winds, more precipitation in some areas, more drought in other areas, and anyway, a wide set of ecological disruptions, which causes finally biosphere damage. And as the biosphere health goes down, policies of different sort are implemented. Of course, it's now a subject of concern. What should those be? Who should do it? Who pays? I mean, this is the stuff of international debates. The models don't tell you how it's going to come out, but they do help you to understand the consequences of the decisions that are made. And the notion here is finally that as the policies improve, it reduces the emissions. But this falsely implies that only humans control greenhouse gas emissions and thus heat in the atmosphere. In fact, of course, there are many other things that are influencing the amount of greenhouse gas increases. I'll give you some examples. Loss of ice cover. As the ice extent goes down, the amount of heat from the sun that's reflected back out of the atmosphere goes down. More heat retains on the Earth, and the heat goes up. It's a positive feedback loop. The more heat you have, the less ice you have, the more heat. Emissions of methane from the tundra. As heat goes up, the tundra begins to melt. It has locked in a lot of methane from past biodegradation, and as that burps out into the atmosphere and stays here for a long time, it traps more heat, which makes the tundra even warmer. At some point, we will saturate the ocean's capacity to absorb heat. And then there will be a flip, and we'll see some really rapid, drastic results. Loss of the boreal forest is another thing which is going to influence greenhouse gases largely outside our control. When that happens, and this is something that we're beginning to face, when that happens, this policy of biosphere health leading to emissions reduction is no longer the dominant factor. We've actually lost the control to influence our CO2 emissions. And now what's really governing the system, area covered by ice, area covered by forest, and other issues. Area covered by ice is reducing as it goes down, reduces the heat radiation. Area covered by forest, as it goes down, also has an impact on emissions. If the area goes down, less CO2 is absorbed by the forest, and so forth. Okay, so that's where we stand, and this is the backdrop now for the discussion about modeling climate change. Modeling isn't going to alter the physical system, but it may have some influence on this policy. And if it does it soon enough, before these other tipping points start to become important, it can reduce the future consequences. If modeling and politics is so slow that it doesn't implement effective CO2 emissions here, we give these other tipping points an opportunity to become dominant. And then we basically get into the back seat and become bystanders and watch how the system unfolds. In 1972, I worked with a team at MIT on a computer model, which led to the publication of the book Limits to Growth. This was the standard model that we published in that book. I'll explain it here. The time horizon, 200 years, from 1900 to 2100. And notice we included a historical period so that we could see whether our model could provide one explanation for what had actually happened, for what we had historical data about. And there's a future period where we trace out the possible consequences of current actions. This is a system which involves many, many social, economic, and other factors impossible for us to predict. They will unfold through conversation, observation, and so forth in ways that science currently has no possibility and maybe never has a possibility to predict. If you can't predict something, then you are reduced to making scenarios, to making different plausible portraits of the future. You can predict an eclipse of the moon to within microseconds. Were I skilled enough, make a mathematical model which would tell you when the moon is going to be eclipsed for any particular place on Earth at any particular time in the future, more or less indefinitely, because the factors that govern the movement of the stars and the planets and the moon are all quite well understood and aren't subject to random influences. In the case of a model like this, where you're talking about non-renewable resources, food per capita, industrial output per capita, persistent pollution, these are parameters governed by billions of individual people, millions of organizations, each operating according to their perceptions, their goals, their resources, and there's no way to predict it. So in our limits to growth analysis, we generated 13 different possible futures. They all look the same during the historical period because, of course, there is only one history. But depending on the assumptions we made, we produced different future curves. This is the one I consider the most likely. Notice here I've inserted a bar to illustrate where we are today, just at the turning point in our 1972 model. What we said back in 72 was that if you continued the policies which were in place at that time, you would continue to see progress in industrialization, progress in food production, and so forth, but at a cost. Resources would be depleted and pollution would rise. Nonetheless, by 2020, we said already back in 1972, you'll probably still consider it was a success. But the consequences of what you've done put in place the seeds for future changes. And as you see here in this one scenario, over the next few decades, food per capita, industrialization, and so forth, quit growing and begin to decline. Population continues on into the middle of the century in this particular forecast, and then declines. Although even in 2100, you have more people, more food, and so forth than you did back in 1900. So this isn't a disaster. It's not the end of the species, but it simply says that the policies which used to work for you quit producing the results you want. It's been easy for some people to look at this scenario and see in it the consequences of climate change. Oh, they say, there you can see what climate change is doing to the population, raising the death rate. This D is the death rate. Unfortunately, the answer is no. In 1972, climate change hadn't become an important item for discussion. In fact, I went back recently, looked at limits to growth, and discovered that it had appeared only once. The term climate change appeared only once in the book. We redid our analysis in 1992, updated some data, and reproduced our scenarios. By that time, there was starting to be growing concern. Jim Hansen had given his famous speech about climate and CO2. And in that book, I noticed we had about 7 references. Nonetheless, still the science was very poor, wasn't our specialty, and it certainly wasn't included in the model. We did our model book again in 2004. By that time, climate change had grown to 15 references. Still, this is not a model of climate change. It's a model of the long-term processes of growth and decline in population, food, and resources. And as I explained earlier, even if it's an excellent model for those things, it's a worthless model for change because the factors which govern the impact of climate change and cause it to occur are just lie outside any of this. They're all excluded variables in this model. Now, if we were to, let me say, I'm coming to the close of my talk. I have one more slide to present, and then I hope that I will have generated a lot of questions that I can deal with. I will deal with verbal questions, but I'll also be reading chat. If it's your preference to write in French rather than English, I'll ask one of my seminar colleagues quickly on a chat bar to translate the French over into English so that I can respond to it. I'll be scanning down that chat bar in just a moment. If I wanted to put climate change into the global model, here's how I would do it. Or rather, I should say, this is where it would have an impact. In fact, you can't put climate change into this particular model. It would be like trying to put a new cog into a Swiss watch. A Swiss watch may do an excellent job let's say, telling you the time. If you suddenly decided you wanted to tell you the phases of the moon and started inserting gears to make it do that, you wouldn't get a better clock. You'd get one that didn't work at all. And I'm afraid that's more or less the same factor here. But I put a few stars just to illustrate the way that climate change interacts with these long-term things. Notice I put here 5 stocks: population, arable land, agricultural capital. This is all the capital which produces food, from fertilizer factories, tractors, farmhouses, irrigation canals, all the industrial capital we put into the production of food and fibers. Pollution, this is long-term pollution like radioactive materials and so forth. And this is the industrial capital. These are the entire stock of capital that produces more capital. Where would climate change enter in? Well, certainly on mortality. We're seeing already the impact of higher temperatures and migrating pests and diseases, increasing the death rate. So there would be some implications for the death rate. Whether or not it would also influence the birth rate is an interesting question. Birth rate tends to be influenced in part by expectations about the future. If you're optimistic, you have more kids. If you're pessimistic, you have fewer. And as the impacts of climate change crank up, we could imagine that expectations about the future may become a little bit more negative. Climate change is certainly going to influence food production. It's increasing the impact of pollution on the agricultural system. Pollution is here broadly defined and includes such things as contaminants in the groundwater and so forth. And it's reducing the productivity of agricultural capital. You can't, hoes and plows and tractors don't produce any human operators. And if the temperature goes to extremes which begin to reduce the ability to use the capital, then the productivity of that capital is actually going down. It's influencing pollution generation and in ways that we don't fully appreciate yet, reducing the productivity of the industrial capital. I mentioned earlier how power plants are attuned to specific temperatures in their cooling water streams. And when the water available begins to heat up, that has an impact on how much you can operate your power plant. But also warehouses located in specific areas, highways cracking, so forth, big impacts on productivity. I've been asked often if I could change this model to include the effects of climate change, and the answer, my really final point, which I'll make today in this formal lecture, is no. It's models are very highly specialized tools. If they're good, they do something well, they don't do other things at all. It's like a hammer. A hammer is a great way of driving a nail into wood. If you want to cut wood into 2 pieces, a hammer is an absolutely lousy way to do it. And you would not be well advised to start trying to modify your hammer so that it could also saw wood. Set it aside and do something specifically for that purpose. And in a moment, Serge, after my talk, will be talking about some other ways to start modeling climate change. So with that, I bring my formal remarks to a close and look forward to the opportunity to have some conversation about these questions.
Well, thank you very much, Professor Meadows,
yes.
for sharing with us your wisdom and your knowledge of long-term global dynamics.